Hello, everybody. Happy Thursday to you. Um, let's see, I'm recording this on Tuesday, and the weather outside looks lovely, but I think tomorrow's going to be weird, which means when you watch this, yesterday was weird. I feel like I'm in a nonstop backwards, forwards time machine as I make these videos, but hopefully they are making sense. Hopefully they are helpful to you as we make our way through this circles chapter. The next thing we have to take a look at is when I have something that is tangent to a circle, and that's actually a term that we've seen before when we did trigonometry, but tangent in this context is going to be a little bit different. Before we get to that, I need to remind you about the Pythagorean theorem. The Pythagorean theorem, we're using it a lot this semester. A squared plus b squared equals c squared. Now, when we learn the Pythagorean theorem, we learn that if something is a right triangle, then a squared plus b squared equals c squared, where a, b, and c are sides of the triangle, and c is the hypotenuse. But it also works in reverse. If a squared plus b squared equals c squared, then we have a right triangle. So for example, the triangle that I've got on the board, I don't have the marking in there that says that it's a right triangle. So is it a right triangle? Is it not? The way that we can figure that out is by sending it through the Pythagorean theorem. Is 5 squared plus 13 squared equal to 14 squared? Well, 5 squared plus 13 squared is 194. 14 squared is 196. Are they equal? No, they are not, which means this is not a right triangle. A tangent line, the definition of our tangent line, at least in this context, is going to be a line that touches the circle at exactly one point. So right now I have a line that's not intersecting the circle at all. This is not a tangent line. If I move it so that it intersects the circle twice, it is still not a tangent line. It's actually a term that we're going to use a little bit later on. This is called a secant line. To be a tangent line, it has to just barely touch the circle at that one point. So this would be what a tangent line looks like, or I could put it over here on this side and have it be tangent to the circle at that point. Or maybe I move some things around. There's a whole bunch of different tangent lines that we could draw. There's another tangent to the curve, a line that touches at exactly one point. Now, yesterday, or actually I suppose 2 days ago on Tuesday, we had two big deal ideas. Today I've got one more to add to it. Big deal idea number 3 is that a line that is tangent to a circle is perpendicular to the radius at that point of tangency. And this again works both ways. If this is a tangent line, then the radius is perpendicular at that point. And on the other hand, if this radius is perpendicular to this line, then it is a tangent line. And so the problems we'll see are going to look something like this. Is this line tangent to the circle? I don't know. We'll have to see if this is a right angle. Well, if it's a right angle, then this would be a right triangle, meaning a squared plus b squared is going to be equal to c squared. Now be careful. This 17 is just the length of this segment that is outside of the circle. We got this part of it also, but since this is a circle, the radius is 10. That means this radius is 10 also. So in this triangle, I've got one side length of 10, one side length of 25, and then a third side length. If this is the hypotenuse, that side length is 27. So there's the question, is 10 squared plus 25 squared equal to 27 squared? Well, plug them in your calculator. 10 squared plus 25 squared is 725. 17 squared is 729. 725 is not equal to 729. So apparently, even though it looks close to a tangent, it looks like it might be, it's not quite. These two numbers are not exactly the same thing, so this is not a tangent to the circle. Let's do another one. You could probably guess what the result is here, but I want to show you what it looks like when it actually works. Same idea. This is a radius to the circle, radius of 6, which means this side must be 6 also. And so if this is a right triangle, if this angle here is a right angle, then it is a tangent line. M is a tangent line, but we don't know until we try it out with the Pythagorean theorem. Is 6 squared plus 8 squared equal to this side squared? Is this a hypotenuse? That would be side length of 10, 6 plus 4. So is it true? Is 6 squared plus 8 squared equal to 10 squared? Well, 6 squared, 36, plus 64 is 100. 100 is equal to 100. So yes, M is a tangent to the circle because it makes that right angle. And we know that that's a right angle because of the Pythagorean theorem. Okay, so that's kind of the big idea there. For a problem that looks like this, and when you look at the homework assignment, you see a lot of different types of problems, but they're all going to have tangents and right triangles and things like that. Um, so here they're saying if n is tangent, so this is a tangent line, which means we know that we've got a right angle. They want us to find this little tiny length right here. How long is segment BC? Well, if I knew how long this side was, I'd be in business. If I knew what the radius of this circle was, I'd be good, but I don't. I know this side length is 12. I know this part is 9, but I don't know what the radius of the circle is. I don't know what this side length is here. Well, guess what? One of the big deal ideas from yesterday was that if this radius is perpendicular to this chord, then it must bisect it, which means if this side is 9, then this side must be 9 also. And so I've got myself a Pythagorean theorem. I've got a right triangle right here. 9 squared plus 12 squared must be equal to the radius squared. 9 squared plus 12 squared must be equal to the radius squared. And so I plug these in my calculator. 9 squared plus 12 squared is 81 plus 144. That is 225. And if the radius squared is 225, then the radius is the square root of 225, which is 15. And now we're in business. Now that I know this radius is 15, all of the radii of this circle must be 15, including this one right here, and also this one right here. Now careful, this 15, that's AC. The rest of this segment all the way out to B is a little bit more than that. And so as I'm doing this, I know this is 15, so I can do a Pythagorean theorem. Again, this is a right angle. We're told that n is tangent, so we can use that. 15 squared plus 8 squared, a squared plus b squared equals c squared. So 15 squared plus 8 squared is 289. And then I take the square root of that to find that AB all the way from here to there is 17. But then we also know that AC was 15, and if AC is 15 and AB is 17, then that little difference right there must be 2. 15 plus what equals 17? So BC, the side that I was looking for, is a length of 2. Moving right along, here's a different looking problem. Given the circle, find the length of x, where 73, we can assume that that is a radius of the circle. We've got a right angle marked here, and then on side x, that's not a radius, it stops at that chord right there. But it's perpendicular to that chord, which means this segment, this radius, I guess it's not a radius, but this chord from the center is intersecting this chord with a right angle, which means it's bisecting. So each one of these parts must be half of 96. Each one of those must be 48. The radius of the circle is 73. So when I moved to this diagram, I drew this radius in there, giving myself a right triangle. And here we go again. X squared plus 48 squared equals 73 squared from the Pythagorean theorem. I did a little bit of algebra and subtracted 48 squared from both sides of the equation, plugged them into my calculator to get 3025. And if x squared equals 3025, then x must be 55 from my calculator, taking the square root, and that is what I was looking for. X in this case is 55. And then one more problem. This one's related to the question that's on the back of the worksheet. I will also say, just like on Tuesday, there are a couple questions that had a whole bunch of different variables that are a little above and beyond what we need to be able to do. I would put this in the same category. There's a question on the back or on the second page of the assignment that has a satellite in orbit around the planet Earth, and there's some different distances. And I like the problem, but I also think it's above and beyond what we need to do. So if you're making your way through this and you want to skip that problem, you can certainly do that. But this problem may help you with that problem. So if you're going to skip that problem, I'll say see you later. If you want to take a look at that problem, or if you just like a little bit more of a challenge, here is this problem for us to look at. This building, this is called the Burj Khalifa, not to be confused with its cousin building called the Wiz Khalifa. It is in Dubai and it is 2,717 feet tall. That's really tall. That's a little bit more than half of a mile straight up in the air, which is pretty impressive stuff. The radius of the Earth is about 4,000 miles. Um, and it's not perfectly spherical, but we're going to go with 3,958.8 miles. And so my question is, how far away, if it's a nice clear day, how far away can you be and still see the top of this building on the horizon? So the idea here is that we are on a spherical planet. So if I look at a cross section of our globe, and then I've got the Burj Khalifa is a building that goes way up in the air. It wouldn't actually look like this. This is exaggerated just so we can see it. But the idea is that if I'm standing over here on the other side of the planet, of course I can't see it. I can't look through the planet. And if I'm standing right over here, I still can't see it because my line of sight is going in this direction. And so I've got this great big window that I can see, but I can't see this because it's hiding below the horizon. So I'm going to zoom in a little bit so we can see a little bit more clearly. Here's the center of the Earth, and then here's the Burj Khalifa sticking out. There's some point this distance away where if I just barely look at the horizon, I can barely see the tip of it rising up. And so that's the question. How far away can I be? What is this distance? How far away from this building could I be? Now, one quick note. I suppose technically we should be looking at the length of this curved surface. Um, but that's a topic for a different day. That's something that we will be able to do eventually, but we aren't there quite yet. So we're going to find this distance right here, this straight line distance, and we will use that instead. And so the way we are going to go about this is by drawing a line all the way from the top of the Burj Khalifa all the way down to the center of the Earth. Now we know the radius of the Earth, or it's given in this problem. We also know the height of the Burj Khalifa. So these two distances together, we can figure that out. And then also I'll draw this segment, this radius from the center of the Earth. And this is the radius of the Earth. We know how long this is. So if I label the stuff that I know, the radius of the Earth, 3,958.8, and then this is 3,958.8 also. In fact, let's copy that over there so I can see it on my diagram. So that's this distance also. And then we've got this additional 2,717 feet. Now, be careful. We're mixing and matching miles and feet here. So when I look at this distance from the center of the Earth to the top of the Burj Khalifa, I've got to add these two distances together, but I got to take into account that one is in miles and the other is in feet. So I could have done this in feet or miles. I chose to do this in miles because this would be an incredibly large number of feet. So I switched over that 2,717 feet. I divided by 5,280 feet in a mile to get that that's a little bit more than half of a mile, 5,146 miles. Excuse me, 0.5146, a little bit more than half of a mile. So I tacked that on to the radius of the Earth, and that is now the length of my hypotenuse. In this right triangle, again, tangent to the circle is perpendicular. That gives me a right triangle. So the radius squared plus x squared, which is what I'm trying to find, equals this distance squared, which is half a mile more than the 3,958.8. Now, these are scary numbers, but you've got a calculator. Plug this in your calculator, plug this into your calculator, and you can do the algebra and solve for x. When I solved for x squared, I got that x squared was 4,074.5. And so I took the square root of both sides of the equation to find that x is about 63.8 miles. Which, when you think about it, like I think about in Burnsville, when you're driving on 35W and you come around the corner, let's see, once you're north of 42, but right before you get to Highway 13, and you can see downtown Minneapolis. And obviously, it's far in the distance, but you can see it from there. You can see these buildings off in the distance. And we're only, gosh, I think we're only maybe 15 to 20 miles away from downtown. So think about driving about 4 times, 3 to 4 times as far away. We wouldn't be able to see downtown Minneapolis, but apparently we would be able to see the Burj Khalifa. So there we go. A little bit of a bonus question for you to try out. Let me know if there are problems as we're making our way through this chapter. Otherwise, we'll keep going. We're going to take a look at some more intersecting segments tomorrow, and well, moving through. We're getting close to the end of the school year, just a few weeks left, and this strange year will be at its end. In the meantime, hope you're having a great day. Let me know if you have any comments or questions, and I will talk to you later. Bye bye.